All right, so yeah, have a look up here. So we're looking at exponential functions, and we've got there the function 2 to the power of x. So this is where we're starting in 12 page. And if you have a look at your notes for 12 page, okay, I've got the summary table there on exponential functions. So an exponential function is some function of the form a to the power of x, and then we're going to change it in certain ways. So we can have some number out the front multiplying it, we can have some horizontal translation, and we can have some vertical translation. So they're all affecting it in the same way, but an exponential function is of the form a to the power of x. So that's where our variable is. So here I've drawn the graph of the function 2 to the power of x, and we could draw it from our calculator. But I mean, what is a graph? So we've got this statement, don't we? Y is 2 to the x, and then you can go, here's x, here's y. X is 0, 1, 2, 3. Okay? So if x is 0, then y is going to be 2 to the power of 0. 2 to the power of 0 is 1. If x is 1, we've got 2 to the power of 1, which is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. And so then you can generate all these points. So this is the first point. X is 0, y is 1. X is 1, y is 2. X is 2, y is 4. So that's how you're generating a graph. Okay. So that's what the calculator is doing when it does it. So I've graphed the function here, that's the first part. Part B says, find f of 0, f of 1, and f of 3. Okay, so f of 0 means when x is 0, we put 0 where the x is, we're going to have 2 to the power of 0, that's 1. When we put 1 there, we're going to have 2 to the power of 1, which is 2. And when we put 3 in there, we're going to have 2 to the power of 3, which is 8. Okay, so that's our answer for B. Part C, use technology to solve 2 to the power of x equals 15. 2 to the power of x equals 15. So on here, we're going to do a G solve. We're trying to solve for x. G solve, x calc. We're trying to solve for x when the value of y is 15. We're saying, what's the value of x when y is 15? And I've got 3.9. 3.906. So 3.91. Okay? And let me explain to you why that's obviously true. Okay, we've got, if we think about x, well 2 to the power of 3 is 8, and 2 to the power of 4 is 16. Okay, that's 2 times 2 times 2 times 2 is 16. And so we're saying, well, what to the power of x is going to equal 15? It's just below 16, which means we expect its power to be just below 4. Okay? And then in part D, it says, state the equation of the horizontal asymptote. Okay, so there's an asymptote here. For all exponential functions, okay, for all exponential functions, they all have the form like this, ax, and I'm just going to put this plus, they've described it as b on the end, as the general form. Y equals b is always the horizontal asymptote. So in this circumstance, we've got 2x, and we don't have anything written here. So that means it's plus 0. We don't have any vertical translation. It's not going up or down, which means the equation of the horizontal asymptote is y equals 0. Okay, so you can determine that just from looking at the equation of the exponential function. Or you can determine it from the graph, okay? And what you can see is, if we just trace along it, as x gets more and more negative, it's getting closer and closer and closer to 0. Okay, so that's our asymptote there. That dotted line that it gets infinitely close to but never passes. So that's the kind of things that you're doing in H, okay? It's a lot of calculator skills. You don't have to do all the questions, okay? So just understand what we've done there, how I've solved these things, how I generated the graph, how we can use our calculator to solve those equations. Make sure you can see the graph using V window, and then the stuff about the horizontal asymptote. Okay, very good. Let's turn the page. Growth and decay. Okay, so this, again, something we have done in Year 10 before, and we can use exponential functions to describe growth and decay of some phenomena. So this is the base equation for growth and decay. Okay, we describe it in terms of population or mass or whatever it is. Population with regards to time, is equal to P naught, which means the initial population times, and then in brackets, 1 plus or minus R, where R is the rate at which the thing is either growing or decaying. And then to the power of T, it's T's time. When we're talking about rates, we're generally talking about time. So consider a population of mice. So the mice are growing. We know they're going to grow because this is positive. Okay, well, it's above 1. It's above 1, so that means it's going to grow. Where T is the time in months. What is the initial population of mice? So that means when time is 0, what is the population of mice? So P of 0 is 2 times 1.15 to the power of 0. Now we can perform bedmass here. 1.15 to the power of 0 is 1. Okay? Any number to the power of 0 is 1, so bedmass, we perform the exponent first. 2 times 1 is 2. Okay, the initial population of mice, 2 mice initially. Of course, there's 1 male and 1 female, and they're going to make lots of other mice. Okay, how many mice are there after 5 months? So that means we're finding P of 5. That's going to be 2 times 1.15 to the power of 5. I'm just going to crunch that. So here, like when you're doing a question like this, you could graph this and you could G-solve all of these answers. 2 times 1.15 to the power of 5. I've got 4. After 5 months, there is 4 mice. I've got 4.022. So we'll round to 4. Okay, how long will it take for there to be 60 mice? 60 mice. So that is when P of T, that is, well, what is P of T? This is the equation of P of T. 2 times 1.15 to the power of T. It's when the population of mice equals 60. We're saying what value of T makes that true. So again, we could use our calculator and we're G-solving for a X value. We could G-solve for an X value when Y is 60. Okay, that's one procedure. Show you another one and maybe follow along with this one so you can familiarize yourself with this skill. So let's go to the main menu. Equation. And then solver. And I've typed in there exactly what I'm trying to solve. 2 times 1.15 to the power of T, or to the power of X, because that's a variable we use in our calculator, to the power of X equals 60. Okay, so I've typed it in, and then you just press solve. And I've got X is 24.3, or T in this circumstance. So after 2 years, 24 months, so after 2 years, there's all of a sudden there's 60 mice. And that's what you'll see the graphs of exponential functions do. They just get massive really quickly. You know, you've heard that term. It's growing exponentially. It's getting big really quick. Now, with equation solver, just be warned, it's pretty useful, but it's not useful when you're solving polynomials because polynomials often have more than one solution, whereas equation solver will only give you one solution. Okay, it's only going to look for one solution, so it'll find one and only give you one of them. So you can use it for certain things, but be wary using it for others. Okay, so that was question 1. Let's move on to question 2 then, which is about a pile of sand. A pile of sand initially has a mass of 5,000 kilos. It's a big pile of sand. So we'll call that the initial population of sand. 5,000 kilos. And it decreases. It's going down. It's decreasing at a rate of 12%. So it's going down 12%. So that's 0.12, isn't it? That's how much it, as a decimal, 12%, 0.12. So then when we're ready to describe the equation, remember this is the general equation of some population. So I'm gonna use N instead, M for mass. I think that makes more sense rather than P, but you could use any letter. So I'm going to say the mass with regards to time is equal to, I'll just write it out first, m0 times 1 take r to the power of t. Now it's 1 take r because it's decreasing, okay? We're taking it away, it's getting less and less. If it's growing, then it would be plus r. And we've got m0 is 5,000, and we've got 1 1 take 0.12 to the power of t. So that's going to be 5,000 times 0.88 to the power of t. So that's the tricky part about this one, is developing the equation. Okay? Okay, that's part A. Find the equation that describes the decay. How heavy will it be after 9 years? Find the mass after 9 years. So m of 9. That's going to be 5,000 times 0.88 to the power of 9. Got 1,582 kilograms. What is the percentage decrease after 9 years? Okay, how much has it gone down by? So I've got a formula there for percentage increase, decrease. Okay, you do the new amount, take the old amount, divided by the old amount. Okay, so our new amount is 1580. So this is the answer to part C. Percent decrease is the old amount, the new amount, take the old amount, take 5,000, divided by the old amount. Okay, and then times 100%. So let's calculate that. 1580, take 5,000, divided by 5,000. I've got minus 0.684, times that by 100%. Okay, it's gone down 68.4%. Okay, and the last part. How long does it take for the pile of sand to halve? How long does it take for the pile of sand to halve? So that is when 5,000 times 0.88. That's when the mass of sand is half its original amount. Originally it's 5,000, so half of that will be 2,500. And I'm going to use equation solver again. So I'll exit out of this. What's my new equation? It's 5,000 times 0.88 to the power of x equals 2,500. Solve. It's going to take 5. What's our time? Years. It's going to take 5 years. I hope I didn't answer months anyway. 5.422. Years. Okay, so like we've gone through a bit there, but I think skills we've sort of had a bit of exposure to before. Let's see how we go with that.
How did you do the